Hey guys, welcome to lesson 1.6 where we discuss the bell-shaped distribution and standard deviation. So there's a large data set of British couple taken in 1980, and one of the categories there is the height of the women. Now, the height of the women ended up being pretty concentrated around 1600 millimeters, and the further out you went, the smaller occurrence of data units. So you can see the shape of that distribution roughly resembles a bell curve. So curve was centered at 1602 and it had a standard deviation of roughly 62.4 millimeters. Now, there are a number of phenomena that occur in nature that kind of follow this distribution. And we can describe that using a mean and a standard deviation. So any sort of bell-shaped curve is centered at some value. So it's centered at some value. Let's call it the mean. And the further out it goes, to the left and to the right from that center, the bigger the standard deviation. So for example, here's another curve, also centered at the mean, but now this one is more spread out. So this one have a bigger standard deviation. So the more kind of narrow and concentrated, the smaller standard deviation, the kind of smaller and more spread out, the bigger the standard deviation. You can think of a standard deviation as roughly, on average, how far are the data points from the mean? So let's look at a specific example to solidify that. You don't need to know this formula, but I do want to go over it so you have a conceptual understanding of how it works. So the sample standard deviation, by the way, a couple of symbols. So mean and standard deviation. So the mean of a population and the mean of a sample. The mean of a population is denoted by mu. The mean of a sample is denoted by x bar. The standard deviation of a population is denoted by sigma, and a standard deviation of a sample is denoted by s. So here I'm looking at a sample standard deviation denoted by s. And we're going to look at four pulse rates: 62, 68, 74, and 76. So for this formula, the first thing I want to do is I want to find the mean. All right, so the mean, I add the four data points, 62, 68, 74, and 76, divided by 4, and I get 70. By the way, n, the thing you're going to see over here, is sample size. So sample size in this case is 4. All right. So we said the concept of a standard deviation is, on average, how far are my data points from the average? So here are my 4 data points. And the first thing I'm going to do, this refers to individual data points. I want to know what is the distance from the mean. So my mean is 70. So 62 is 8 to the left of the mean. 68 is 2 to the left of the mean. 74 is 4 to the right of the mean. And 76 is 6 to the right of the mean. Now we're going to square all those. So negative 8 squared, negative 2 squared, 4 squared, and 6 squared gives us that. And I want to find the sum of those squares of differences, which will be 120. All right, so now I've completed this part of the formula. Next, I divided by sample size minus 1. Sample size is 4, minus 1 was 3. So 120 divided by 3 is 40. So the only thing I have left to do to find the sample standard deviation is find the square root of that whole thing. Square root of 40 is 6.36. Nope, 6.32. So that is my sample standard deviation. The empirical rule says that for normal distributions, approximately 68% of all data falls within 1 standard deviation, 95% of all data falls within 2 standard deviations, and 99.7% of all data falls within 3 standard deviations of the mean. So with a distribution that has a mean of 1602 and a standard deviation of 62.4, we would expect 68% of all data to be 1602 plus or minus 1 standard deviation. So we would expect roughly 68% of all women to be within 62.4 of 1602, which would be 1539.6 and 1664.4. And we would expect 95% of all women to be within 62.4 times 2, within 2 standard deviations of the mean. And then we would expect 99.7% of all women to be within 3 standard deviations of the mean, which only leaves 0.3%, so roughly 3 out of 1,000 women, to be shorter than 1414.8 or taller than 1789.2. So very rare occurrence to be outside of 3 standard deviations away from the mean. So here is kind of how some of this math checks out. And basically, this kind of corroborates the fact that this data does fit a standard normal curve fairly well. All right. Z-scores tell us how many standard deviations and in what direction an observation is from the mean. So the formula for z-scores is my observation minus the mean divided by my standard deviation. So data values that have negative z-scores will be to the left of the mean, and values that are above the mean have positive z-scores. So positive z-score, you're to the right of the mean. Negative z-score, you're to the left of the mean. Let's see how this plays out. So by the way, a standard normal curve is centered at 0 and has a standard deviation of 1. So it's centered at 0, standard deviation of 1, which means 68% of data is between -1 and 1, 95% of all data is between -2 and 2, and 99.7% of all data is between -3 and 3. All right, so use the z-score formula to answer these 4 questions. I have my mean at 1602, my standard deviation at 62.4. I know this is from the sample, but I'm just going to use the kind of z-score formula of x minus mu divided by sigma. I know this is population, but we're just going to use that for this. So find the z-score of a woman whose height is 1550. So z-score is the height of the woman, 1550, minus my mean of 1602, divided by my standard deviation of 62.4. And that gives us negative 0.83. All right, could that make sense? So this tells us that we're to the left of the mean. So 1550 is to the left of the mean. And it tells us we're less than 1 standard deviation from the mean. So yeah, and 1550 is less than 62.4 to the left of the mean. So yeah, that looks good. A z-score of a woman whose height is 1625 millimeters. All right, so 1625 minus 1602. How many standard deviations is that from the mean divided by 62.4? And I get 0.369. So not even 1 standard deviation to the right of the mean. What about a height of a woman whose z-score is negative 1.25? So now I'm 1.25 standard deviations to the left of the mean. So negative 1.25, and I want to find the height of that woman. So 1602 divided by 62.4. So using our middle school algebra, we're going to multiply both sides by 62.4. So negative 1.25 times 62.4. And I'm going to add 1602. That's going to isolate x on the right side. So when I do that, I get x is 1524. Is that a plausible answer? So 1524 is to the left of 1602. Good, so it's going to have a negative z-score. And it's more than 62.4 away, so looks good. The height of a woman whose z-score is 2.25, so this woman is 2.25 standard deviations to the right of the mean. So this woman is 2.25 standard deviations to the right of the mean. And that will be 1742.4. That's the height of the one. So take the mean, add 2.25 standard deviations to it, and that's it. All right, so that's a quick overview of the bell-shaped curve, the idea of a standard deviation, and how we use z-scores given a mean and a standard deviation for some sort of distribution.